Objectives and goals for this lab include conducting a sensitivity analysis in order to show the dependence of NTU and HTU on liquid and gas flows, characterizing the mass transfer coefficients by plotting them as a function of gas flow rate, in addition to comparing them to literature correlations. Additionally, we will use Aspen Plus to simulate ammonia absorption, and then we'll determine the pressure drop as a function of flow rate and use it to characterize column flooding.
Absorption is the chemical process by which mass is transferred from a gas phase to a liquid phase. It occurs in a packed column if the column diameter is less than 2 feet and the packed height is less than 20 feet. If the column is too tall, channeling may occur. This is when the liquid solvent is flowing down the column wall and the gas is flowing up the center. Basically, it means that the liquid and gas are not in contact. To minimize channeling, packing diameter should be less than 1/8 of the column height. A good absorbent has a solute that has high solubility in the solvent. The solvent has a low volatility to reduce loss of the solvent. It is not corrosive, toxic, or flammable, and in this lab, the solvent is water. In the figure, an absorption column is shown. The liquid goes in the top of the column and through a distributor that helps prevent channeling. The liquid then comes out the bottom of the column. The gas goes in the bottom and comes out at the top. As packing size increases, mass transfer efficiency decreases and pressure drop decreases. There exists an optimal packing size that gives a high mass transfer efficiency and a low pressure drop. In a packed column, there are two different kinds of packing: random and structured. In this lab, 3/8" ceramic rashing rings that are randomly packed are used. Table 6.3 shows a comparison of the different types of packing.
Film theory forms the basis for mass transfer coefficients. Film theory starts with Fick's law, which is shown in the equation below. In this experiment, the liquid phase is dilute, so we can neglect the bulk flow effects and write the Fick's law in terms of the diffusivity divided by the film thickness. In practice, it is difficult to measure this, so we write the Fick's law in terms of mass transfer coefficients rather than molar fluxes. The units of the mass transfer coefficient depend on the driving force used. To obtain overall mass transfer coefficients, we must use two-film theory. In two-film theory, the rate of mass transfer is equal in both phases. For the vapor phase, we can write the flux in terms of the partial pressure driving force, and for the liquid phase, we can write the flux in terms of the concentration driving force. Solving for the partial pressure at the interface for the vapor phase, and for the concentration at the interface for the liquid phase, we can combine these two equations using Henry's law because we are in the dilute regime. After combining these equations, we obtain an equation for the overall flux through both phases, which gives us the liquid phase mass transfer, overall mass transfer coefficient, as shown in the equation at the bottom. We can do a similar process to obtain the overall mass transfer coefficient for the vapor phase. The Henry's law constants used in this experiment were obtained from experimental data found in Perry's Chemical Engineering Handbook. To obtain these values, the partial pressures must be converted to Y values by dividing by the system pressure, which in this case is atmospheric pressure. From this data, the Henry's law constants can be determined by regressing an expression shown below. This gives us the Henry's law constants over a range of temperatures. These figures show a summary of the data obtained from Perry's Chemical Engineering Handbook. The left figure shows the equilibrium data at various temperatures, and the right figure summarizes how the Henry's law constant changes as a function of temperature.
Packed absorption columns do not have physically distinguishable stages, and therefore provide continuous contact between the liquid and vapor phases. Because there is not a set number of trays, mass transfer models, rather than equilibrium models, are used to describe absorption. The material balance around the top of the column is shown below. In this equation, Yn represents the concentration of ammonia coming into the column, and Y out represents the concentration of ammonia leaving the top of the column in the vapor phase. This model assumes that the solution is dilute, making L and V constant. The equation below solves for the concentration of ammonia into the column. Based on two-film theory, the rate of mass transfer per unit volume is given by the equation below, which equates the rates of mass transfer for the liquid and vapor phases. Because it is difficult to measure the interfacial concentrations, they are eliminated and overall mass transfer coefficients are used instead. In order to find the overall mass transfer coefficients in terms of the local mass transfer coefficients, some tedious algebra is done. The equation for this is shown below.
To obtain an equation for the length of the packing in terms of the height of a transfer unit and the number of transfer units, we must start with the differential material balance. The differential material balance is given by the equation shown here, where V is the molar flow rate, dy is the change in composition, Ky times A times the mole fraction driving force is the mass transfer rate per unit volume, S is the cross-sectional area of the column, and dl is the change in height. Integrating this differential mass balance across the length of the entire packing gives the following expression for the length in terms of HDUs and NTUs. To obtain a usable expression for the number of transfer units, we must first eliminate the fictitious vapor phase concentration using Henry's law. After plugging this in, we must then eliminate the mole fraction in the liquid using the material balance derived around the top of the column. Once this has been done, the integral can be taken and the expression for the number of transfer units can be obtained as shown here. This can then be plugged back in to the equation for the length of the packing. In this equation, we know everything but Kya, so we can solve for the height of the transfer units and in turn the mass transfer coefficient.
The experimental mass transfer coefficients were compared to two correlated values. These two correlations are the ones that we chose to use. It is important to note that these two correlations give the local vapor and liquid phase mass transfer coefficients and therefore must be converted to overall mass transfer coefficient values. It is important to know which mass transfer coefficient you are using and in what units. Use this table as a guide to help determine what units each of the variables is in.
The biggest safety hazard with this lab is the presence of ammonia gas. It is very flammable and causes severe skin burns and eye damage, and it's also toxic. The OSHA PEL is 25 parts per million, and the odor threshold is 5 to 50 parts per million. To reduce the risks associated with ammonia, the experiment will be carried out in a fume hood, and the lab instructor will be the one to operate the ammonia cylinder. We will also be wearing proper PPE, which includes safety goggles, closed-toed shoes, and the lab coat.
In order to prevent the ammonia analyzer from being damaged, the water level in the bottom of the column should be kept below the analyzer. In order to raise and lower the level, you use this arm over here to adjust.
Seen here is a figure of the apparatus used in the experiment. As you can see, there are 4 temperature indicators as well as a pressure indicator. The values read here are communicated with the LabVIEW software. Additionally, the water flow is controlled with a rotometer, and the ammonia and air flows are controlled with valves.
To adjust the airflow into the column, use the needle valve here. The resulting airflow rate will be read on the display. To adjust the ammonia flow rate, use the needle valve here, and the resulting flow rate will be read on the display here. To adjust the rotometer, turn the knob here, and be sure to get it eye level to accurately read the level. This is the ammonia analyzer, and the reading is displayed here. The reading should not exceed 1,000 parts per million, or the ammonia analyzer will have to be reset. The column is filled with random packing, and the packing is 3/8 inch ceramic rashing rings. Here the packed height is 2 feet. There are 4 temperature probes throughout the column, at the bottom and the top, and 2 in the middle, and those values are reported to the LabVIEW software.
The inlet of the vapor, or the air, in this apparatus comes in at the bottom of the column. The liquid, which is water, comes in at the top. At the top of the column, there's a liquid distributor to help the liquid fill the entire column instead of just running down the sides.
To calibrate the rotometer flow, Hannah will first close the ball valve, letting water into the column, and open the ball valve, letting water flow down the Teflon tube into the bucket. She will then adjust the rotometer value to 40, and then we will take various points to calibrate the rotometer.
To calibrate the flow meter, we'll use the bucket method. With the bucket method, I will take the water flow, let it fill up the bucket, and measure the time it takes. I will then look at the subsequent mass that filled the bucket, which has already been tiered. This will give us a flow rate and will be repeated for subsequent rotometer values.
The results of the rotometer calibration are shown in the figure. The rotometer value is plotted on the x-axis, and the mass flow rate is plotted on the y-axis. After the experimental data is plotted, it is fit with a line of best fit, and the equation of that line is used to calculate the mass flow rate at all rotometer values.
After the rotometer calibration is performed, it is important to input the calibrated values into the LabVIEW software. You'll do that under where it says Enter Water Rotometer Reading. This will be the slope of your linear fit, and this is the intercept. In order to check the pressure calibration, use this manometer to read the height difference, and then compare it with the heights read in the LabVIEW software.
First, we turn on the water flow to the apparatus by opening the white handle of the ball valve.
Next, turn on the airflow by opening the ball valve.
Now we're turning on the LabVIEW software. We're now going to have Dr. Schneider turn on the ammonia flow for us.
We have water flow going, and I will turn on the ammonia, smell for any leaks. There aren't any. Then I will go ahead and introduce ammonia to the rest of the column. And connect the tubing to the ammonia detector. And you're good to go.
To perform a run in this experiment, first you set the rotometer and the airflow to the desired values. Then you use the needle valve right here to adjust the ammonia flow to obtain an inlet concentration of 950 parts per million. Once it comes to steady state, then you measure the top and the bottom concentrations to determine the absorbance of ammonia.
To read the ammonia inlet and outlet compositions, you adjust this valve. To read the outlet compositions, you have the arrow pointing towards the top of the column, and to read the inlet composition, you turn the valve towards the bottom of the column. In order to determine the pressure drop, the procedure is to set the water flow using the rotometer, log data at the airflow equal to 0, find the airflow that results in flooding, and then vary the airflow between no flow and flooding flow rate. Each time you will log the data in order to determine the pressure drop at each flow rate.
Each of the runs was simulated in Aspen Plus and was compared to the experimental data. The outlet ammonia concentrations as a function of vapor and water flow rates for both the experimental and simulated cases can be seen in this figure. Even though the simulated and experimental values differ from each other, they both follow the same expected trends. Ammonia outlet concentration decreases as vapor flow rate decreases and as the water flow rate increases. The simulated values of ammonia outlet concentration are consistently higher than the experimental data. These results suggest that the mass transfer coefficients calculated by Aspen were lower than the values used in the experimental data analysis. Additionally, a few other approximations made in Aspen could have contributed to this discrepancy. First, the inlet stream temperatures on the simulation were specified as the temperature measured at the bottom of the absorber. To improve this, temperature probes should be placed on the apparatus at the inlet streams before they enter the absorber. Also, the measured air and ammonia flow rates were converted from volumetric flow rates to mass flow rates using the ideal gas law before entering them in Aspen. These values will be slightly different from their actual values, which also contributes to the difference between the simulated and experimental values. A sensitivity analysis was performed in Aspen Plus to determine the effect of vapor and water flow rate on outlet ammonia concentration. The results are shown in this figure, which confirms the experimental trends that outlet ammonia concentration increases as gas flow rate increases and decreases as water flow rate increases. The effect of vapor and liquid flow rate on NTU is shown in this figure. As seen, for a constant liquid flow rate, an increase in vapor flow rate causes a decrease in NTU. This decrease occurs because the contact time between the vapor and liquid phases is decreased. As the contact time decreases, the vapor moves faster through the column, and therefore mass transfer has less time to occur. Also in the figure, it is shown for a constant vapor flow rate, an increase in liquid flow rate causes an increase in NTU.
In the figure, the effect of varying flow rates on HTU is shown. As expected, increasing the air flow rate increased the height of a transfer unit. This trend is exactly opposite that of the NTU. This was expected because the NTU and HTU are inversely proportional from one another. Overall, the observed trends reflected the expected trends in the calculation of NTU and HTU. Because the two variables are inversely related, as one value increases, the other must decrease. Additionally, the decreasing trend in NTU accurately reflects the decreased contact time when vapor flow is increased.
This figure displays the overall vapor phase mass transfer coefficients for the flow rates of interest. As seen, for a constant liquid flow rate, increasing the vapor flow rate causes the mass transfer coefficient to increase as well. This increase showed that an increase in vapor flow corresponds to more efficient mass transfer. However, as the vapor flow was increased, the contact time between the liquid and vapor phase was also decreased, resulting in less overall mass transfer. In other words, by increasing the vapor flow rate, the rate of mass transfer from the vapor to the liquid was increased. Although not as much mass will be absorbed, the amount that was absorbed will be absorbed faster. Additionally, for a constant vapor flow rate, increasing the liquid flow rate caused an increase in the overall mass transfer coefficient. This trend was expected as more liquid present in the column means that more mass transfer absorption can occur. A larger mass transfer coefficient represents this increase in absorption activity.
The experimental results for column pressure drop are shown below. The calculated pressure drops were correlated with the following equation. The experimentally determined pressure drops were consistently higher than the correlated values. Additionally, the correlation better fits data at lower liquid flow rates. However, while the correlation better fits these liquid flow rates, experimental results depart from the correlation for vapor velocities at or above 20 meters per second. This departure from the correlation is in part due to column flooding. At a consistent liquid flow rate, a continued increase in gas velocity will lead to flooding conditions. In this figure, flooding conditions are shown by the sharp increases in pressure drop at high gas velocities. Similarly, for a constant gas velocity, flooding conditions occur when the liquid flow is increased.